Hello, I'm Ziyi, SHOU, a PhD student at the Hong Kong University of Science and Technology, Hong Kong. Today, I will be presenting our STAR-SEM paper, Incorporating EDS Graph for AMR Parsing. My co-author for this paper is Professor Fangzhen at the Hong Kong University of Science and Technology. Let us begin. All things semantic are receiving heightened attention in recent years. Discrete and hierarchical structured semantic representations play an important role in making sense of natural language. Here are some example mini representations for the same sentence. We can see that despite for the same sentence, different mini representations vary a lot. Mini representation is based on the idea that the meaning of the sentence can be expressed in a formal structure. Within the field of mini representation, graph structured framework is a major area of interest for its adequate target structure for downstream applications. A mini representation graph is defined as a triple N, E, and T, where N is the set of nodes and E is the set of edges. The in and out degree correspond to the number of edges arriving or leaving nodes respectively. Those nodes that has 0 in degree are defined as top nodes. They are always the main predicates. There are hundreds of mini representations, to name several: DM, EDS, or AMR. We can classify different flavors of mini representations based on anchoring. Anchoring means the relationship between the written sentence and the nodes of the mini representation graph. It's also referred to as alignment or correspondence. Flavor 0 here is the strongest form of anchoring. Each graph node is directly linked to one specific token. For example, DM is in flavor 0. And flavor 1 is more general. It allows nodes in mini representations to correspond to any part of the sentence, whether it's a subtoken or a multi-token. Here, EDS is in flavor 1. And flavor 2 refers to the mini representations that are simply unanchored. AMR is in flavor 2. In our experiment, we try to incorporate EDS to AMR graph. So first, let's see more details about EDS. EDS encodes minimal result semantics in a variable-free semantic dependence graph. As we can see from this figure, nodes in an EDS are labeled with semantic predicates. For example, here, important, and of, and the dollar n and 1. The edges in an EDS are labeled with a small set of rows that indicate the relation between a predicate and its argument, or a quantifier like BV. AMR was proposed by Benariska's group in 2013. The idea of AMR is to abstract concepts from words and work only on concept level. The nodes in an AMR graph are annotated with AMR concepts, which also can be concrete or abstract. A concrete concept can be a sense-tagged predicate. For example, important -01. The edges in an AMR graph are annotated with AMR relations, most of which can be viewed as semantic rows. For example, here argument 1 represents the object of the predict. Here is the comparison between EDS and AMR. From previous introduction, EDS is in flavor 1, while AMR belongs to flavor 2, which means EDS has an explicit many-to-many anchoring onto substrings, while AMR is simply unanchored. The predicate node in EDS consists of a lemma followed by a cause part of speech tag and an option sense label or a particle. Nodes in AMR is high-level abstraction from service token. They are mostly from prop bank, another semantic corpus. Edges in EDS are used to provide a numerical ID for the arguments of predicates that occur in a sentence, and they are not interruptible. Interpretable. In AMR, the semantic role for each argument is defined for a specific sense of predicate in prop bank, and can thus and can be interpreted. From the results on MRP 2020, the parsing accuracy for AMR are in low 80s, while they can be high 90s for EDS. It brings to the motivation of our work. AMR parsers do not perform as well as the one for EDS, and EDS is anchoring, but AMR is unanchored. The topology of the AMR is quite similar to EDS. Therefore, EDS parsing may serve as an intermediate to AMR parsing. Our method is as follows. First, we reconstruct EDS graph to include service tokens, and then feed new graph into a graph encoder to produce token-level features. This allows we combine the EDS features to word embeddings and use in AMR parser. The first step is to reconstruct the EDS graph. Original EDS graph doesn't include service tokens. In order to produce EDS features for each token, we add a bottom layer consisting of the input sentence tokens here. For new added nodes, we add edges named as contain between token nodes and the original nodes if their spans of strings intersect. These edges are labeled as to contain. We propose an EDS graph encoder composed of LSTM layer and GCN layers. The LSTM layer is to capture context information, and the GCN layers are designed to encode the structure knowledge. To reinforce the relation between nodes through layers, we add self edges for every node in the graph and the inverted edges phi and phi for each directed edge phi to phi. EDS annotation in this experiment is automatically generated by EDS parser. So accepting all information from the EDS graph is risky. Therefore, we adopt gate scheme. More details for the formulation can be found in our paper. So after getting EDS token level features, we combine the features to word embedding. Finally, we feed the combined word embedding to our adopted AMR Parser, HITSCIR, which was the best overall system at MRP 2019 and the second best for AMR. It's a transition-based system and use stack LSTM to model transition states. The original model used BERT for EDS embedding, while we use EDS enhanced embedding. We perform our analysis on MRP 2019 dataset. The top part is the official results for 4 systems achieving competitive results in MRP 2019. The middle part is the result for our baseline model. And the bottom part plus EDS are our proposed EDS enhanced models. We note that All our 5 EDS enhanced systems perform better than our baseline HIT-SAIR. Our best model is one bias TF layer plus one GCN layer. And we can see from the result, the number of GCN layers matters, but it's not necessarily the more the better. Here are the results for the Little Prince dataset. This tested dataset contains 100 random sentences from the book The Little Prince, which are least similar to the training data. What is worthwhile noting is that our models, which are basically HIT and SAIR enhanced with EDS in variable layers, boost its performance on the Little Prince significantly. In conclusion, we propose EDS incorporation methods for AMR parsing. The improvements are especially noticeable on the Little Prince tested dataset, which is out of domain. Given the many representations, we believe our graph encoder with LSTM and GCN layers can be applied in other downstream tasks. More generally, whether there is a universal semantic parser that can take advantage of information from each framework is an interesting question worth investigating. Here is the reference list. So thank you for your interest in our paper, and please feel free to contact us on my email for any clarification or suggestion.